Hello everyone. So today we are going to start a new topic which is excited state dipole moments. It will come under the unit that one is photochemistry, and for that we will be going to just go through some slides which are I will give a rough idea during this video what you will be going to cover, what I will be going to cover, share with you. So firstly, this is the title slide. Then I will be sharing two videos with you. The first video is for how the red green color of water during the Raman spectrum changes to red color. Then the another slide will be for Raman spectrum. It will be just basic and for your basic understanding. Then the importance of Franck-Condon principle and how the overlapping is most important for the Franck-Condon principle. That Franck-Condon states that vibronic transition will occur when the wave function overlap is maximum. So in this slide we will be going to cover that. Then in the next slide it is again the Franck-Condon principle in simplified form, and it is a video covering the Franck-Condon principle. Then we will be going to start the topic, that is excited state dipole moment, and this is the syllabus for your same three syllabus of photochemistry unit. And before going to start that topic, that is excited state dipole moment, we are going to cover the difference between dipole moment and polarizability. So you should know that. And this will how the solvent polarity affects the dipole moments when the solute remains present in ground state as well as in excited state. Here solute will be the fluorophore molecule which will be showing the fluorescence when it comes from higher excited state to the lower excited state. Sorry, when it will come from the higher excited state, that is first singlet state, to the ground singlet state. So during that, what will be the changes that will be occurring? We will be going to cover this. The next will be the same thing. Then we will be going to cover all the slides. Here, just remember the diagram that firstly, equilibrium ground state, it is at lower level as compared to the Franck-Condon ground state, and Franck-Condon excited state, it is higher level as compared to the equilibrium excited state. Just remember this diagram. And these are the different slides which will cover the how the derivation comes, and you will get the derivation where you will be putting the value of mu a, that is the wave numbers, and you will get the equation, and from that equation you will derive the value for del nu bar. And when you will draw a slope, when you will draw a graph, you will get the value from slope, that is mu a minus mu g, that is you can calculate the value for dipole moment. So this is a very powerful method for determination of excited state dipole moments. And at high viscosity, low temperature, or at high temperature, what are the changes that are occurring? We will be going to cover that in these slides, and these are the references which I will show you. And here we will end with the slide. So as just we all know, as we all know that how spectroscopy is important, how absorption emission spectra are important. Likewise, what are the changes associated with the photochemical transitions for that have to be seen under the topic photochemistry. So let's start the topic. Here I will share off my button. I will be sharing only the screen now. Hello. So today we are going to go to the next topic of photochemistry, which is excited state dipole moments. Before going to discuss that topic, let's study some basic concepts through some videos. So,
When a substance is exposed to laser light, nearly all of the scattered light produced is Rayleigh scattered light. However, a very small percentage is Raman scattered light. Because the percentage is so small, this light is invisible to the naked eye. However, with the use of certain tools, this light becomes visible.
And only 0.001% of the light when that filter is being applied there, at that time you can see the red Raman scattered light can be observed. That is the green color changed to the red color. As you can compare both the lights, Rayleigh scattered light is being in red green color and Raman scattered light has been obtained in red color, which is a weak red light. So
This is the
this is the
spectrum
spectrum
of
of
scattered
scattered
light from
light.
the sample. Because we are using a 532 nanometer excitation wavelength, we can detect both strong Rayleigh scattered light at 532 nanometers
So here you
and
can see
weak
that
Raman
the
scattered
Rayleigh
light at a
scattered
longer
light is
wavelength.
being obtained at a wavelength
Light
of
at 532 nanometers is visible as
532
green light.
nanometers,
Therefore, at first, a strong green light was
because of
observed.
which you will
Raman
obtain a
scattered light, on the other
red
hand, is
intensity
too
band,
weak to be
a green
seen.
intensity band.
Next, by using the filter,
Now,
Rayleigh
when we are
scattered
going to
light at
use the
532
filter,
nanometers is
at that
blocked.
time this
Now, the
red
Raman
green
scattered
light
light
was being
emitted at a
transferred
longer
to the
wavelength is
red
visible.
portion, and you will
This is
obtain
the
the
Raman
Raman
spectrum of
spectrum of
water.
water.
When
Initial
using
spectrum
an
was Rayleigh
excitation
spectrum, and this
wavelength
is
of
the Raman spectrum.
532 nanometers, the Raman peak of water appears around 650 nanometers, the wavelength of the color red. That is why the Raman light was visible as red light. Usually, the horizontal axis of a Raman spectrum is indicated by wave number, not wavelength. By using wave number, we see the Raman spectrum of water independent of the excitation wavelength.
So you got the concept, where the green intensity band has been changed to the red intensity band on the application of filter, and that's why Raman spectrum of water comes to be in the red region. This is the Raman shift, which for water, which can be obtained at a wavelength of near about 3500 centimeter inverse. Now, this is one again, when we are watching, when we are saying about the Raman spectrum, then what is, you have already been seen in your earlier BSc syllabus, what is the Raman spectrum? As Raman spectrum gives three types of lines, that are Rayleigh lines, then Stokes lines, and anti-Stokes lines. Just to recall all those concepts, I have taken this video. Just go through the video.
Used in analytical instruments like filters, monochromators, as well as some different
You
detectors.
can get the link
We
of
have
this
also
video where
covered
they have
different UV
described the
visible
different
instruments
instruments
and fluorescence
and how they
spectrometers in
work.
our previous videos. If you have missed
It
these
will be
videos,
helpful for
check
you
out the
for
link in
the
the description
paper 2
for the
syllabus,
playlist
which is
on
on
analytical
instrumentation.
instrumentation. In this video, we will discuss the principle of Raman effect
Now
and
let's
understand
study
how
the
it can be used in
principle
Raman
of Raman
spectroscopy
effect.
to perform analysis on a given sample. Let us first understand the Raman effect. When a sample is exposed to monochromatic light in visible region, the sample absorbs light, and major portion of the light gets transmitted through the sample.
Now
However, a minute part of the
you can
light
see
is
some
scattered by
absorption
the
is occurring,
sample
some
in
transmission
all
is
the
occurring, and
directions.
some part of radiation
One
are
can
being
observe
scattered in
the
at a
scattering
direction of
at
90
right
degree.
angle to the incident
Just you can
beam.
observe it. It is
The
at the
incident
direction of
light
90
has
degree.
a particular
Scattering
frequency.
occurs at a
If the
90
scattered
degree.
light has the frequency same as the incident light,
Then it is
then the
called as
scattering
the
is called as
Rayleigh
Rayleigh scattering.
scattering. Scattered
However,
frequency equals to
it has
incident
been
frequency.
observed that about 1% of the total scattered intensity occurs at frequencies different from the incident frequency. This is called as Raman scattering. Raman scattering can be thought of as two-photon process. The electrons have different vibrational levels. They are defined by specific energy differences. When an incident monochromatic light interacts with an electron in the sample, the electron absorbs energy from the incident photon and it rises to a virtual state of energy. The energy transferred is given by the formula E equals h nu, where nu is the frequency of incident photon. The electron then falls back to an energy level by losing energy. If the energy lost equals to the energy of incident photon, the electron falls back to its initial level and in this process emits another photon. Since the energy lost is equivalent to the energy of incident photon, the released photon has same frequency as the incident photon. As the frequency is same, Rayleigh scattering occurs. However, sometimes electrons, when losing energy from the virtual state, can fall back to a different vibrational level. In this case, the energy lost by the electron is different than the energy absorbed from the incident photon. As a result, the photon emitted by the electron has energy different than the incident photon. This is possible when the frequency of the emitted photon is different than the incident photon. This gives rise to Raman scattering. Depending upon the final energy of the electron or final vibrational level of electron, Raman scattering can be separated into Stokes line and anti-Stokes line. If the frequency of scattered photon is less than the frequency of incident photon, Stokes lines are observed on Raman spectrum. This happens when the electron absorbs energy. Similarly, when frequency of emitted photon is greater than incident photon, anti-Stokes lines are observed. This means that energy is released by the electron. The Raman spectra gives the molecular fingerprint and it is different for different molecules. By studying the spectra, one can identify the rotational levels and thus a particular molecule. This helps in performing qualitative analysis. Similarly, the intensity of a particular Raman line helps one determine the concentration of a molecule in a sample. In this manner, quantitative analysis can be done. Thus, Raman spectroscopy can be used to perform both qualitative
quantitative analysis. Now, the next concept you should be having, which is the Franck-Condon principle. It is a rule in spectroscopy. Franck-Condon principle is nothing but it is just a rule in spectroscopy and quantum chemistry that explains the intensity of vibronic transitions. That vibronic means the vibrational transition associated with the electronic transitions. So how those vibronic transitions occurs and their intensity can be explained with the help of Franck-Condon principle. Now, vibronic transitions are the simultaneous changes in electronic and vibrational energy levels of a molecule due to absorption or emission of a photon of the appropriate energy. The principle states that during an electronic transition, a change from one vibrational energy level to another will be more likely to happen only if the vibrational wave functions overlap more significantly. Means the wave functions should must overlap so as the transition to occur. Let's have as you can see, these are the different wave functions as you have already studied it in the quantum chemistry chapter. So here these are the different wave functions. This is associated with 1s where there is no node. This will be for 2s where there will be one node. This is associated with the 3s where there will be the two nodes. So these are the different wave functions for particular orbitals. Now what happens here, this is the internuclear distance and this is the energy axis. As you can see, these are the E0 and E1 here. These are the electronic energy levels and these electronic energy levels are being associated with the different vibrational energy levels. Here they have mentioned 0 to 6 energy vibrational energy level for the ground state as well as the 0 to 6 energy levels for the excited state. Now, these are the normal ground state as well as the normal excited state. And there will be also the Franck-Condon excited state and Franck-Condon ground state. You can see it, we will see it later. So here you can see if the molecule is being absorbing the radiation at that time, where should it reach? It will have the option. When it is being absorbing some radiation at that time, it will have the possibility to reach to different energy levels. But where the overlapping is maximum, the wave function should have the maximum overlapping. There only the transition will be possible. Now here you can see this second vibration energy level can overlap with that of the zeroth ground state energy level. So because of this, the intensity of this band will be higher as compared to the other bands or other transitions. Now, also when the molecule is being coming from excited state to the ground state at that time also the maximum overlapping should be there, and where there occurs the maximum overlap, as you can see here also there is overlapping occurring, here also there is slight overlapping is occurring, here also there is slight overlapping, but there at the second energy level you can see there is maximum overlap is being possible. So the intensity of excited state vibrational energy level to the second ground state vibrational energy level will be highest. So we will see it in the next. So this is same. What is Franck-Condon principle? It is a fundamental principle of absorption spectroscopy first, and according to this principle, in the molecule electronic transition is very fast at a range of 10 to the minus 15 seconds. As you can predict the lifetime, that is 10 to the minus 15 seconds. The molecule is coming from ground state to the higher state on the absorption of energy, and within the time of 1 minus 15 seconds it is coming to the ground state. So the molecule in the molecule electronic transition is very fast. That's why, as we know, the atom is composed of, or the molecule is composed of nuclei as well as the electrons. Now when we are saying that is occurring the electronic transition. So electronic transitions would be associated with the nuclear transitions also, but the electronic transitions is occurring at a very high speed of 10 minus 15 seconds. So nuclei doesn't give that time for the transition to occur, because of which the nuclear position will remain unaffected there. So, and as it is a less time, there is no chance to move nucleus, means position, and hence momentum remains same before and after the transition. So there is no change will be in the nuclear distance. That's why this is the distance. And electron goes in the higher energy state, as you can see from zeroth level to it is going to the higher energy state level. So this principle is used to represent the intensity of vibrational electronic spectra, which is also called as the vibronic spectra. You can get the video for this Franck-Condon principle. I have taken a smallest video here. Just take a look on this video. Now, I have got the video from the YouTube. It is about the Franck-Condon principle, explaining the different things. So, as you can see, molecule will absorb the different amount of radiation, as a result of which it will go to the highest energy level depending on the absorption energy, and when it will be coming to the ground state at that time, where it can come. So what are the possibilities of maximum overlapping of the wave functions that have to be seen during the fluorescence? We will study the Jablonski diagram for that again. So here in Franck-Condon principle, it states that an electronic transition takes place so rapidly that vibrating molecule does not change its internuclear distance appreciably during the transition. So there is no change in internuclear distance as the transition process is so fast. The electron absorbs a photon and goes in excited state, and it returns back to the initial state within the millisecond of 10 to the minus 15. So This principle is used to represent the intensity of vibrational electronic spectra. The vibration of the electron energy of a diatomic molecule with the internuclear distance is shown. So this is the vibrations of energy of a diatomic molecule with the internuclear distance. This is given. So let's have a look on the video.
Franck-Condon principle. Franck-Condon principle states that an electronic transition takes place so rapidly that a vibrating molecule does not change its internuclear distance appreciably during the transition. There is no change in internuclear distance as the process is so fast. The electron absorbs a photon and goes in excited states and initial state within a millisecond, that is 10 to 15. This principle is used to represent the intensity of vibrational electronic spectra. The vibration of the energy of a diatomic molecule with internuclear distance is shown in the figure. If a diatomic molecule undergoes a transition into an upper electronic state in which the excited molecule is stable with respect to dissociation into its atoms, then we can represent the upper state by a Morse curve similar in outline to that of the ground electronic state. There are three cases in the Franck-Condon principle as shown in the figure. Case 1. The internuclear distance at the potential energy minima in the two electronic states is almost equal, which means internuclear distance in the ground state is similar to an excited state dot, and the two curves lie almost one above another. The 0, 0 band, in this case, is the most intense as shown in the figure. The change in the position or velocity during the electronic transition increases as one moves toward higher values of vibrational level. In the case of 0, 0 band, the overlap integral involves two bell-shaped functions leading to large intensity, whereas 1, 0, 2, 0, and so on bands involve many positive and negative contributions to the overlap integral and so have lesser intensity. Case 2. The potential energy curve of the upper state is shifted to larger values of R. That is, the internuclear distance of the upper state is larger than the lower state. In this case, the most probable transition that conforms to the Franck condition is no more the 0 to 0 transition. The intensity of vibration first increases from the 0, 0 value to a maximum and then decreases for higher values of V prime means higher state because overlap integral has a maximum value when the maximum or minimum of the upper wave function lies almost vertically above the maximum of the lower eigenfunction. Case 3. When the potential energy curves of the two electronic states are shifted by still larger values. That is, the upper excited state has a very larger value than the lower state. In this case, the most probable transition will be from V double prime equal to 0 to a state with larger values of V prime, that means an upper excited state, which may even correspond to the continuum. The overlap integral will be large only for larger values of V prime means upper excited state. Thus, from the above discussion, the most intense transition is the one that occurs without change of internuclear distance, or more clearly that the transition which occurs in accordance with Franck-Condon principle must be of greater.
So here, the most intense transition is one that occurs without the change of internuclear distance, or more clearly that transition which occurs in accordance with the Franck-Condon principle of greater intensity. So you have seen the three cases where that RE dash equals to 0. RE, these both RE and RE slash and RE double slash equals to same. Then RE is greater than RE and this is 2 greater than this. So what will be the possible effects for that? You can see the video again. Now, we are going to start our unit, and the main topic for this is about the excited state dipole moments. Now, as we are going to see the dipole moment and polarizability. What is the difference between the dipole moment and polarizability? For that, I have taken this video. So just have a look on this video. As we have already seen, you already know what is the dipole moment and what is polarizability. Just have a look on the video again.
Explain the polarizability of molecule. When the molecules are placed in the electric field, there are the separation of electrons and the positive charges. The molecules or atoms which are spherical are now in the field are converted into elongated form. Now there will be separation of charges and they are pointing towards the respective plates. Now the dipole moment will be generated inside the atom or molecule. This dipole moment is called induced dipole moment or mu I. The induced dipole moment is directly proportional to strength of electric field applied. Therefore, mu I is proportional to E, where mu I is induced dipole moment and E is the strength of the electric field. Therefore, mu I is equals to alpha E, where alpha is polarizability of the molecule. Therefore, polarizability of the molecule is defined as induced dipole moment per unit strength of the field applied. That is, when E is equals to 1, then mu I will be.
So here you can see the difference between the dipole moment and the polarizability factor. When the molecule is being applied to some electric field at that time, the nuclei come towards one side and the electrons come towards the excited side, because of which there occurs the formation of two poles, and this is called as the dipole. And if this is the electric field which is being applied, then there comes some factor of polarizability, and it is the polarizability. So this is the polarizability is the induced dipole moment per unit strength of the electric field applied. Now, solvent polarity. Now, increasing the solvent polarity, if you go on increasing the polarity, dipole moment should increase, and along with the dipole moment, there will be some changes in the polarizability factor also, depending on the electric field which is being applied, which causes a red shift in the fluorescence, as we have seen the earlier video where the green shift has been shifted to the red side for fluorescence. So here, initially, the solvent dipoles are being aligned with the fluorophore molecule. Red one is the fluorophore molecule, and these blue are the solvent molecules. Now, you can see the alignments. Now, when these absorb some amount of radiation at that time from the ground state, they will go to the singlet force excited state, and in that state you can find that the fluorophore molecule changes its pole. So the excited state fluorophore and solvent dipoles are being now unaligned, which are initially in the alignment position. They have been unaligned to themselves. Now they will take a vibrational relaxation time of 10 to minus 12 seconds and will come to some lower excited state, which are called as the triplet state. So this is the solvent relaxation, which will for where the molecule will stay for the 10 to minus 10 seconds, and during this the dipole moments again gets realigned themselves. As you can see, the dipole moments of the solvent have been aligned themselves with that of the fluorophore molecule, and from that state it will come to the ground state. So this is not the triplet state. This is the just from higher state to the lower vibrational state the molecule is coming, and from that lower vibrational state it will come to the ground state, and at that time it will emit some amount of radiation, and those radiations which are coming from the singlet force excited state to the singlet ground state, these are called as the fluorescence radiation. And if these are going through the triplet state, and from that triplet state it is coming to the ground state, then that will be called as the phosphorescence. For that you should just read the Jablonski diagram. Now this is the lifetime versus solvent relaxation. This is again the same thing. Just we will read out it. The time scale of the solvent relaxation. The time scale of the solvent relaxation, it depends on the mobility of the fluorophore solution envelope, which is the viscosity. If it is lower, if the viscosity is low, comparable to the fluorescence lifetime, then emission from the non-relaxed state contributes largely to the spectrum. So this is the lower the temperature, the higher will be the viscosity, and the smaller the redshift of the emission spectrum will be obtained. Because the solvent, when we say about the solvent, at that time we will have to take some factors like dielectric constant of the solvent, then refractive index and the viscosity. These three factors have to be taken into account. So this is the singlet ground state, then this is the singlet Franck-Condon excited state, this is again the relaxed Franck-Condon excited state, and the molecule is coming to the ground state, where initially they are having the green shift, and that green shift changes to the red shift during emission, which is of lower intensity. So again the same thing, how they have been explained the same thing in different manners. For that I have just taken the pictures. Now just we will move towards our topic. So all this we have earlier seen, that was just the basic, that will not be asked in your exam. The topic for your syllabus is the excited state dipole moments, how the dipole moment align themselves in the excited state, as we have seen in the earlier pictures. Initially the molecule will remain aligned with, that is the fluorophore molecule remain aligned with that of the solvent molecule, and when it goes to the excited state it gets de-aligned, and while coming back to the lower vibrational energy state it gets again realigned to itself with that of the solvent entity, and then it comes to the ground state with the realignment position, and during this there occurs the change of green band towards the red band. Now, and all this is because of the effect of solvent. So the effect of solvent on absorption and emission spectra give useful information regarding the physical properties as dipole moment changes and polarizability of the molecule in the two combining states. So the theories have been worked out in terms of Onsager's theory of dielectrics and Franck-Condon principle. According to this, the energy shift between the 0 to 0 band in absorption and emission spectra, that is from green to the red, is related to dielectric constant of the solvent, refractive index of the solvent, and difference in dipole moments of the solute molecule in the two combining energy states. The short range interactions here are being neglected, which are the hydrogen bonding interactions. Now, when you take a look on this, you can see that is del E, the energy difference associated in the absorption state as well as the fluorescence state. That is, this is the absorption energy and this is the fluorescence energy. It depends on the dielectric constant of the medium, then it depends on the refractive index of the medium and dipole moment of the medium, where you can see what is E. So mu G and mu E here, these are the ground state as well as the excited state dipole moments, and A is the radius of the cavity in which solid molecules resides, as the solvent molecule will be surrounding the solute entity, so that radius. For this you can watch my video for same 4, which is about the collisional quenching and optical quenching. So the latter is defined by on-cycle reaction field, assuming the solvent as continuous dielectric. Now, the shift in 0 to 0 band due to solvent interaction in the two states of different polarity. The states are being of different polarity is explained with the help of Franck-Condon principle for absorption and emission spectrum. Now you can easily get all these concepts as you have already seen the basics. So this is the equilibrium ground state. This is the Franck-Condon excited state, where you can see these things, and the molecule will be coming to the lower vibration energy state, excited state, but so from that it will be coming to the Franck-Condon ground state, which comes to be at higher position than that of the equilibrium ground state. So effect of refractive index and dielectric constant of solvent on 0 to 0 transition of polar molecule can be explained with the help of this diagram. So in the ground state, a solid molecule is having a dipole moment of mu g. It is residing in a cavity of radius d in the medium of static dielectric constant capital D, and the reaction field R0 produce on such interaction. That is the reaction field which is being produced for the interactions of the solvent with that of the fluorophore entity can be given as R0 is equal to twice mu g upon A cube in bracket D minus 1 divided by twice D plus 1. And if S0 is the unperturbed Weber phase energy level of the molecule in the ground state in solution, it is depressed by an amount proportional to R0. So this is the same diagram. As you should have greater look on it as you will be watching it on mobile. For that I have again taken the same diagram. Now, on excitation, the molecule is promoted to the ground to the Franck-Condon excited state, and in that excited state, the dipole moment may not only have a different magnitude but the different directions also. Since the electronic transition is much faster than the dielectric relaxation time, the ground state solvent orientation will not have the time to change in tune with the new situation. So only the electronic polarizability is affected immediately on excitation, and that's why we see there will be no change in the nuclear position. So the reaction field, that is a Franck-Condon state, is we have already seen the R0, that is reaction field, and this is the Franck-Condon reaction field, will be equals to twice mu g upon A cube n square minus 1 divided by twice n square plus 1. Where n is the refractive index, n square is equal to the high frequency dielectric constant of the frequency of absorption, and the energy of absorption will be given as energy of absorption will be h mu a is equal to h mu a naught plus Franck-Condon excited state, normal reaction, Franck-Condon reaction field, normal reaction field, and the associated dipole moments with the excited state and the ground state. So this is the energy of complete absorption, which is being taken in the two forms, where mu a naught is the energy in the gas phase. This is the gas phase energy. Now, if the average, there are two conditions when the fluorescence lifetime is more than that of the dielectric relaxation time. So if the average lifetime, that is TF of the excited state, is greater than that of the dielectric relaxation time, then the excited state dipole moment polarizes the solvent, and the solvent molecule adjusts to the new situation. What they say, if TF is greater than that of TD, then mu E, that is dipole moment, will polarize the solvent, and the solvent molecule adjusts to the new situation, and a reaction field will be given by the equation that twice mu E divided by A cube in bracket D minus 1 twice D plus 1 is will produce the Franck-Condon excited state Fc star is stabilized to give the excited state S1, and here the 0 to 0 fluorescence transition occurs from this energy state, and a straight ground state is produced with the Franck-Condon principle, in which solvent orientation does not change with the does not have time to change. And in this case, RFC, as the solvent orientation does not have time to itself to change, so in Franck-Condon state, it will be equal to twice mu E upon A cube in bracket n square minus 1 divided by twice n square plus 1. So this will be the Onsager's field. What have you seen here? If TF is greater than that of TD, then mu E will polarize the solvent. And as the solvent will get polarized, it will adjust with the new situation. And in that case, the reaction will be field will be given by this equation. Now the Franck-Condon energy state, it will be then stabilized with that of the excited state S1. As you have seen the figure earlier, that Franck-Condon state is being in equilibrium with the excited state S1. And 0 to 0 fluorescence transition occurs from this energy state. Again, a strained ground state. Again, you just recall that figure where you have seen the ground state, Franck-Condon ground state is being produced with the Franck-Condon principle. And for that, then the reaction field will be having the expression, this one. The dielectric constant will be replaced by the refractive index. Now, this is the equation which we have already written, that is mu A, that is the energy of absorption, will be divided into two parts. This is the gas phase energy and this is the reaction field energy associated with the transition. So the energy of 0 to 0 transition in emission, as you have seen the earlier thing in the earlier slide, the molecule will be coming from the fluorescent, that is the Franck-Condon excited state to Franck-Condon ground state. In that case, the energy associated with that fluorescence will be given by h mu f. Just replace the things of frequency with mu f. So h nu f is equal to h nu f0 plus rfc minus r star, and this is the mu a minus mu g. So finally, the Franck-Condon ground state relaxes to the equilibrium ground state. Just how that diagram which I have shown you in the just one slide before you should, in your mind, there should be the picture of that diagram so as to take this. So the difference between 0 to 0 absorption and 0 to 0 fluorescence energies. So here the difference between the absorption and fluorescence 0 to 0 energy band is obtained from the two relationships, which is 4.11 and this 4.14. Assuming that this value and this value, these are equals, then when we are going to equate these equations at that time, the values will get cancelled and we will get HC, that del nu bar, that is VA minus VF, and C will be the, as nu is being replaced, we all know that is frequency is related with the wave number with this factor. So HC nu bar will be equals to H epsilon in bracket VA minus VF, and placing that value of VA minus VF, this is HC is equals to HC del nu bar is equal to HC, and del nu bar is nothing but will be equals to V nu A bar minus nu F bar. So these are the wave numbers for absorption energy band and for the fluorescence energy band. So as the C factor will get cancelled out, in that case, we will have the equation. These equations have to be, as these have been cancelled out, when you are going to write the two equations and replacing the values at that time, finally you will get that the equations, that is R star Fc minus R naught, and this plus value again will get minus. So minus plus minus plus minus. So RFC minus R star. So just you are going to this the value is inside the bracket will be minus, and this value is already minus, so minus minus plus factor will be there. So plus R star in bracket mu E minus mu G. As these are the constant factors, you just go on write this and you will easily get how they have derived the equation from these two equations. So we have obtained the expression in wave numbers, that is Hc del nu bar will be equals to this factor. These are the fluorescence reaction field in Franck-Condon excited state, Franck-Condon ground state, and the reaction field. So already we have obtained this equation. Now from the earlier derived equations, that is 4.12, 4.13, 4.15 and 4.16, the final expression for del nu bar will be equals to this much value, which is twice in bracket mu g minus mu e minus mu g bracket square hc divided by e cube in bracket d minus 1 divided by twice d plus 1 and square minus 1 twice and square plus 1. Just combine all these equations and you will come to this equation. So this is equals to, again, the factor of E, the factor for this is being del f. So they have taken the value for that is del f. And here, where is my pointer? Pointer has changed the color. So here del f is equal to this value, and the remaining value for del nu bar will be in the simplified form will be this one, that is twice h nu minus mu g, sorry, not h nu, this is mu e minus mu g, dipole moment in the ground excited state and ground state bracket square hc. H is the Planck's constant, c will be the velocity of light, a will be the distance through which the solute is being fluorophore molecule is being surrounded with the solvent, and del f will be this constant factor. Now here for non-polar solvent, that capital D, dielectric constant and the refractive index are nearly equals, and also the interaction energy will be equals to 0. So the factor will be gets cancelled out. Now when we draw a graph of del nu versus that of this value, as you will know, y is equal to mx plus c. So here, this, how they have plotted this, this is your x-axis, this is your y-axis, and so the slope will be obtained for this value, and that can be calculated, and this is the del f factor. So this is x value, this is y value, and mu e, if mu e is greater than that of mu g, then a positive slope will be obtained, and if mu e is being less than that of mu g, then a negative slope will be obtained. And these are some values for the different compounds for mu, del mu, mu g and mu e. Those have been obtained. So this technique is very useful to determine the excited state dipole moments, which can be obtained from the graph. So we have seen that is if TF is being greater, if TF is less than that of TD. Now at high viscosities and low temperatures, TD is greater than that of TF. That is, TD value will be greater than that of TF. So in this case, there will be the decrease in the 0 to 0 separation between the absorption and emission spectrum. On the other hand, at higher temperatures, at low temperature, there will be decrease in the 0 to 0 separation band. And at high temperatures, there will be TD will be decreasing, and there will be the 0 to 0 separation may again decrease. At high temperature also it will decrease, and at low temperature also, because of high viscosity, it will decrease. And a maximum value for del nu 0 to 0 is expected at some intermediate temperatures. So besides the relaxation effect, the 0 to 0 separation can also be affected by the environmental modifications of the potential energy surfaces. So these are responsible for the variation of photochemical behavior of a molecule, that as the 0 to 0 separation can also be affected rather than the temperature factors, they can also be affected by the environmental modification of potential energy surfaces. So they are largely responsible for the variation of photochemical behavior of a molecule in different solvents, and because the order of energy level may change with the change of the solvent where the transition is being occurring. So many such examples can be represented in the appropriate places. So these are the references which I have taken for the different YouTube links. You can watch those videos. So this is the again quote through which I want to end the lecture, that God does not give us all we like. God gives us everything that is good for us. So whatever we are having, that is good for us. We may be expecting very interesting things, very different things, but they are not be very useful for us. God always gives us which is useful for us and which is best for us. So always remember, nature is at its best, and whatever is happening is all because of our karma, and it is also best. So have a good life, have a good day. Thank you. This is a quote from Brahma Kumaris to which I follow, that never hold your head high with pride or ego. And whatever position you will be, or you may be, and you are, never hold your head high with pride or ego. Remember, even the winner of a gold medal gets medal only when he puts his head down. Just always have a smooth behavior to everyone. All souls in the universe are equal and they are special ones. So give the special treatment to every soul. Never discourage anyone through your acts or deeds. So thank you. I hope you like the video. Just watch it twice, thrice so as to clear the concept. Thank you. Okay, the topic is being found quite difficult. So just watch the video twice, thrice so as to get friendly with the topic. And thanks for watching. We will meet again at 12:45. So take a break and get prepared for the next video. Take out your lunch. Thank you.